Okay, but you got to be a little careful about that. You can't say you accept your null hypothesis just because you were unable to prove that it was false. Okay, so that you just failed to reject it. That's how you would state that. Okay, so now let's go to our second example, the second way that we did this, and take a look at the same problem from the perspective of a smaller sample size, from a sample size of 25. So I'm going to take this and I'm going to copy this over. It's the same null hypothesis. Okay, except this time we had a sample size of 25. Okay, so now in this case, I can't use Z. Now this time I'm calculating a t distribution. Okay, I can, word is funny. It always makes me capitalize the first letter. I should really turn that off. It's the most annoying thing in the world. T is equal to, and it's going to X bar, just like before, minus mu, the mu for the all others, okay, divided by the standard error. So in this particular example, let's work this out now. X bar was 648 minus, I'm not going to bother with putting parentheses in as if it's going to calculate it. I'm trusting you to understand what I'm subtracting first and then dividing by and so on and so forth. Minus 620, the mean, divided by the standard error. In this case, it turned out to be 12. Okay, so that's equal to 28 divided by 12. Okay, so let's see what 28 divided by 12 is. 28 divided by 12 is equal to 2.3. I'm going to round it off to 2.3 for our purposes. 2.3. Okay, so we're 2.3 standard errors apart for our t-score. If this had been a z-score, I could say I could reject the null hypothesis. Can I reject the null hypothesis now in this situation? What do you guys think? Do I know yet whether I can reject the null hypothesis? Do I even know whether I can or not yet? We don't know. Well, you're saying no. We don't know. When you say no, you're saying that we don't know. I hope you're saying that you don't know if we can reject the null hypothesis because we haven't really tested it yet, have we? Okay. In order to test it, we have to go over here to our t-table and find out what our critical value is for this sample size. Okay, and again, sample size of 25, 24 degrees of freedom. Our critical value for 2 is 2.06. Did we exceed 2.06? Well, we did, right? So that means that in this case, we can reject our null hypothesis and accept our alternative hypothesis. Had the result been 2.01, we would have failed to reject the null hypothesis. Even though it's more than 1.96 and would have worked for the z-score, we can't reject it for the t-score because we haven't exceeded the t-score that we need to exceed, the critical value of t for that particular sample size. How do you guys feel about that? Are you comfortable with that? Okay, good. I think you guys are getting this, and I think that this is going to be valuable to you as we move in. Okay, I just want to talk about one more thing as far as these proportions are concerned, or as far as these the t-test and the confidence intervals are concerned, and that is proportions. Okay, so I'm going to talk about proportions now. I'm going to start with a fresh piece of paper. I can go back here, and I'm going to talk about proportions. Okay, so I'm going to take a situation where we have a population that has a let's say we're testing a drug that treats acne, for instance. Okay, so let's say that we know in this population that the proportion P, the actual population proportion for a particular population is 25%. 25% of teenagers have acne in this population. That's P, an actual population proportion or prevalence. Okay, let's say I decide to take a sample of 100 teenagers, and I give them a special cream that we invented or something like that. And I find that the proportion for our sample of 100 teenagers, P cap I'll call it, I can't draw that little cap, so I'll call it P cap. P cap is equal to, P cap's kind of like X bar, right? It's our sample proportion, not our population proportion. Our sample proportion is equal to, let's say, 15%. Actually, I'm going to make it a little higher. I'm going to make it 16%. Actually, I'm going to trick you first. See if I can trick you first and make it 10%. Okay. Now I want to calculate my confidence interval. I calculated my proportion, my P cap for those 100 teenagers, and I found that it was 10%. I want to calculate a 95% confidence interval for that for the population of teenagers that might be using this cream. Can I use this sample now to do a confidence interval? So everything has to do with sample size. Okay, no, I can't, because when I have a proportion of 10%, I have 10 teenagers that have acne and 90 that don't. I need 15 on each side of that proportion. I'm going to change that. I would need a bigger sample size. For instance, I would need a sample size of, say, 200. Because if I have a sample size of 200 with a proportion of 10%, well, then I have 20 that don't have it, don't have acne, and I have 180 that don't. So I have, on each side of the proportion, I have 15 people. I won't try and trick you on an exam with something like that. I will, if I give you a proportion, find a confidence interval for it, do a t-test on, I'm not going to try and trick you and give you something that you can't legally do it on. But just so you know that you need that sample size, and that's one of the justifications for using the Z distribution for proportions instead of using the T distribution for proportions. Okay, let's calculate the 95% confidence interval for this. Well, just like before, the way we do a confidence interval is we take our point estimate, our mean, in this case our average, our proportion, P cap plus or minus, right? The Z score that we need for a 95% confidence interval. Okay. Now remember that if it were a 99% confidence interval, we'd use a different number for Z, wouldn't we? Right? We would use, for 99, we would use 2.68 instead of 1.96, because they got to be further apart to be 99% certain you captured the true population mean for all the cream using teenagers. Okay, so let's say plus or minus the Z score for our alpha of 0.05 times our standard error. Okay, so how am I going to calculate that? Well, first thing I want to do is I want to calculate my standard error. How do I calculate my standard error from this sample? And is the sample big enough for me to calculate a standard error? Well, it is, because by default, if you can do the calculation, you have at least 15 people in each group, you have 30. So you're always dealing with a large sample size when you do this kind of calculation for a confidence interval, legally at least anyway. Okay, so what's our standard error going to be equal to? Well, it's going to be equal to the square root of, guys, remember the formula? P times 1 minus P, right? All of that on top over N. And then we're taking the square root of this whole nasty thing. Everybody comfortable with that? Pretty silly looking? Okay, let's do it. The standard error is going to be equal to the square root of P. What is P? P is 0.1 times 0.9 divided by the sample size, which is 200. And then we're going to take the square root of that whole Megillah. Okay, so that's going to be equal to the square root. And I got to do the top first, right? I'm going to do 0.1 times 0.9 is 0.09, right? 0.1 times 0.9 is 0.9 and move the 1 over, so it's 0.09 over 200. Okay, so I'm going to get my calculator out. Okay, so I'm going to clear this. I'll clear the memory. So it's 0.09 divided by 200 is equal to this. It's a really small number. And then I'm going to take the square root of that. Square root of that is 0.02. Okay, I'm gonna round off for my purposes. You try not to round off as severely. 0.02. Okay, that's going to be my standard error. Okay, so now I'm going to use my standard error in this formula for PCAP, for confidence interval PCAP. So our confidence interval is going to be equal to 0.10, our sample proportion, plus or minus, right? Now, what am I going to use for Z here? What value am I using for Z? I'll address that question in a second. Guys, what value am I using for Z here? 1.96. Yep. I'm going to address that question in just a second. Karen has a great question there. I'm going to address it in just a second. Plus or minus 1.96 times my standard error, which is 0.02. Okay, I'm going to, again, just simplify things so we don't spend too much time on this. I'm going to call that 2. So 2 times 0.02 is 0.04. So our 95% confidence interval is going to be 0.1 plus or minus 0.04. So our confidence interval is going to be 0.06 to 0.14. So we're 95% sure, based on this, we're 95% sure that the true population mean, population proportion for teenagers that use the cream is between 0.06 and 0.14, right? Now, why did I use 0.10 instead of 0.25? When I'm looking at the confidence interval, I really don't know that. All I know is my one sample, right? There's no reason for me to know what the if I'm doing a confidence interval, there's no reason for me to know what the proportion of that other group is. So the only thing I know here is that my sample of 200 people, I had 20 people that had acne, I had 180 that didn't have acne, so I had a proportion of 10% for my population. So the only P I know is the P cap, right? So I really don't know anything else about the population. That's why I use that for the our our situation. Well, hang on a second. So we use P cap for P because we don't know P. We don't know what the proportion is for this population that uses the cream. We only know what happens for the 200 kids that use the cream. Okay, we don't know all kids that are using the cream or will use the cream, for instance. Okay, since we don't know the 0.25, there's no way for me to do it. Just like with our sample before, I didn't know what the mean was, right? I only knew what X bar was. Okay, so now let's say that we want to compare this. We want to do a single sample t-test here, and we want to compare this. We want to compare this to a known population mean. Okay, so let's see how that might work. Well, the way that would work is just like you did before. You say the t-score for this comparison is equal to, instead of x bar, p cap, minus p, the known population, mu, where will be mu before, right? And I'm going to divide that by the standard error. Okay, so now let's see what our t is going to calculate out to. T is going to be equal to, see the difference between P cap and P. Let's see, P cap and P. Well, P was 0.25. I erased it there, didn't I? Equals 0.25, right? And P cap is 0.1. So it's 0.1 minus 0.25 over the standard error. Okay, now let's talk about what our standard error is. The standard error, now I have to make a decision, don't I? How am I going to calculate this standard error? Should I use P cap to calculate the standard error, or should I use P to calculate the standard error? Okay, well, the bigger the number is that I use to calculate the standard error, like if I use 0.25 instead of using 0.1, for the standard error, for the distance apart that these two are, that's a more conservative estimate of the standard error. Why is that? Because when we multiply 0.25 times 0.25, we get a bigger number, bigger standard error, than if I multiply 0.1 times 0.09. If I multiply 0.25 times 0.75, I get a bigger number than if I multiply 0.75 times 0.25. I don't think it's likely I'm going to give you an example where you're going to have to do a t-test for a proportion, but you might want to consider that if when you calculate standard error, maybe it's more appropriate to use the larger proportion in all cases rather than the smaller proportion to do a more conservative estimate of whether you can reject the null hypothesis. Okay, so in that case, we would base our standard error on, okay, let's see, it's going to be 0.25 times 0.75 divided by the sample size, which is 200, okay, and let's see what that's going to come out to be. Square root of the whole thing. Square root. I'm going to tell you something interesting about poles now in a second. Calculation. 0.25 times 0.75 equals divided by 200 equals square root of that is going to be equal to 0.03. So in this case, our standard error comes out to be equal to 0.03. Okay, so let's calculate what our t-score is equal to. Our t-score is equal to, excuse me, our c-score. I don't need t-score, I need z-score here, right? Got away from me there. Our z-score is equal to 0.15, the difference between these two, 0.15 divided by 0.03, which is equal to 5, right? So our z-score is equal to 5. Now, what's our critical value for z? What is our critical value for z? How big does z have to be to reject the null hypothesis? 1.96. So z, z because we're using a proportion, doesn't have to be a, because we're always going to have a big sample size. What's considered a big sample size when we use a proportion. Okay, and the more conservative one, we use the population proportion for the standard error. It's more conservative. It's going to be harder to reject the null hypothesis. What did I forget to do here, by the way, guys? Would you let me get away that you're supposed to do first thing before you do anything else? What'd you let me get away with here? I didn't propose a null alternative hypothesis. Right, yeah. So what's H null? And what's H alternative? Anybody want to propose an H null for this t-test? Right? What is that going to be? That's going to be P, the proportion for proportion for non-cream using teenagers is equal to P for cream using teenagers. And what's our alternative? That's not true. That they're not equal. Okay, that the two proportions are not equal to. Again, I'm using population proportions in my null and alternative hypothesis. Okay, one other thing that I want to point out here, and that is that that's our null or alternative hypothesis. I wanted to point out that you just heard me say that it's more conservative to use the population proportion because we actually know what that is, and it happens to be a bigger number in this case also. Okay, so when you see polls done, the elections are coming up, and pretty soon you're going to see polls that say that Chris Christie has 11% of the vote, 0.11, and Paul has 10% of the vote, and Trump has 2% of the vote, or whatever, whatever it actually really is. And they're all going to say margin of error, right, is plus or minus 0.03, say 3%. Well, how could they have, look at this, they have all different proportions for each one of these guys. How could they have a same margin of error for each one of these guys in the poll, right? How did they come up with something like that? Well, the reason why they have that is because what they're doing is remember, the margin of error is really just another way to say our z-score times our standard error, right? The reason why they do that, yeah, exactly. You couldn't tell for sure. You wouldn't be able to tell for sure. Remember that the margin of error is, you wouldn't be able to tell for sure that they were different, because they really could, another poll really could be anywhere from 7 to 13 with 95% certainty. And Christie could be anywhere from 8 to 14. So Christie could actually be 8 and Paul could actually be 13, for instance, right? So, but they're all doing better. We all know that, but they all are different enough from Trump to be able to be pretty certain. In other words, if you did a t-test between Paul and Christie or Paul and Trump, then you would reject, hypothesis, say they're not the same. Okay, so notice that they use a z-score. So the z-score is going to be 1.96 because, as usual, they want to be 95% certain as most of us want to be, right? But for the standard error, when they do the calculation for standard error, they're using the sample size, right, that they took. But what they're doing is that they're always using, for the p-value, they're always using 0.5 times 0.5, right? Why are they using 0.5 times 0.5? Because 0.5 times 0.5 is equal to 0.25. You cannot get two numbers like 0.4 times 0.6 or 0.3 times 0.7. None of the other numbers, once you get one of these two that are smaller than the other, p and 1 minus p, once there's a difference, you'll never get a value for the top of this equation that's bigger than 0.25. So to be conservative, they just use 0.5 and 0.5 for the p values, the p and the 1 minus p that they use to calculate, to determine the standard error in calculating the margin of error that they report for the polls. And that's why they always have, no matter which proportion it is, they always have the same margin of error. They just use this for their margin of error for everybody. Okay, it's kind of like a little trick that they do. Okay, so that's where we stand with that. So now, I'm not going to ask you to do proportions with SPSS. However, you might come across a situation where you might be asked to do proportions for a t-test or a z-test for SPSS. Now, I want to point out one other thing that we did with the z-score over here. Okay, and that is when we determined the z-score here, right, where we had our sample size was 36, we had enough confidence in our standard deviation to, substitute it for the population standard deviation, and we wound up with a z-score of 2.8. So now we know that since it's bigger than 1.96, we know there's less than 5% chance of being wrong if we reject the null hypothesis that these guys are the same. Okay. However, when you have the z-score, you now have the ability to go to the z-table. I'm going to go to the z-table. Okay, let me see if I can find it. Here's the z-table. You now have the ability to go to the z-table and actually look up a z-score of 2.8. 2.80, I'm going to look at it here. And 2.80 represents a area under the curve to the left of that value, to the left of, I'm looking at the negative side right now, to the left of this of 0.026. If I go to a positive 2.8, it's going to give me 99.8%. So this is going to be 0.02 to the right of this also. It's going to be symmetrical. So that's why I'm only going to bother to go to the left and then just double it. Okay. The probability that we would get this big a z-score or a bigger z-score is only I'm going to round this off to 0.03, 0.003 is only 0.3%. That's the probability we would get this extreme of value. But since I also haven't accounted for the top part of this, I'm going to double that and call it 0.06, 0.006, or 0.6%. So the probability of being wrong, if we reject the null hypothesis, is less than 1%, is actually 0.6%. So I could actually calculate, if I do a z-score, actually calculate a p-value or probability of being wrong if I reject the null hypothesis. Right? That's the actual probability is really 0.006. Okay, when I use the t-score, I don't have that latitude. When I use the z-score, I just have a single number that tells me if I can reject or accept the null hypothesis. That's a little bit of a twist. There's ways you could use that table to kind of bracket the real probability, but for our purposes, for right now, all you have is that number. So all you can say is that we can reject the null hypothesis with our probability of being wrong less than alpha, or in other words, less than 0.05, even though it could be much lower than 0.05, could be 0.01, could be 0.006, right? But it's hard for us to tell that because we only have that single, the table that we have only has that single value, our critical value. Okay, so does that make sense to you guys? Does it make a little bit of sense to you guys? So the z-score allows us to actually calculate a probability of being wrong. Now, SPSS has the latitude to be able to calculate the exact probability for t, because it actually calculates the t values and the probabilities every time it does it. It doesn't use anything over 30. I'm going to use the z table. It actually calculates it for every sample size, even if the sample size is enormous, like 10,000, and the t-score would be 1.9600001. It still uses that instead of using 1.96. It always uses the t-distribution to calculate this because it has the ability to do it without putting a lot of effort into it. Okay, so in other words, if I go to SPSS, let's see if it's working still. Cross your fingers. Okay, if I go to SPSS and I do a t-test, okay, I'm going to just go through this real quick and then we'll call it a night. I'm sorry we got started so late on this. And thank you guys for sticking in there, hanging in there, for this long and keeping the faith that I would be here eventually. I think they might be throttling me because I use Netflix too much. Although I'm not sure if that's against the law for them to throttle me or that. Maybe I'm using too much bandwidth and they don't like me, or maybe I have a neighbor that's downloading stuff at this time of the night. Hopefully this will start up shortly so we can continue. I'm not going to ask you to do proportions here. Yeah, I'll get it up sometime tonight for sure. I'll get it up sometime tonight for sure. So you'll definitely have access to it by the morning as well as for this. I'm not sure how quickly I can get it up and running. I want to make sure it's working well because it's going to be hard to reach me tomorrow night. So I want to make sure that it's working, so you guys don't get tripped up on it or something like that. Okay, come on, SPSS. I think we're about there. Usually it's about there. In the meantime, I'm going to get a list of numbers from somewhere else. There we go. The p-value. The p-value is the probability that you would be wrong if you reject the null hypothesis. Okay, and your acceptable level of error, acceptable level of chance of being wrong, is typically, say, something like 5%. So usually in most studies, you'll accept a level of chance of being wrong if you reject the null hypothesis of 5%. So as long as your probability of being wrong is less than 5%, less than alpha, in other words, P, probability of being wrong is less than alpha, 0.05, you reject the null hypothesis. And that takes place when the critical value for T or Z, right, is greater, when the value that you calculate for your T or Z is greater than the critical value for Z or T. Critical value for Z is always 1.96. So as long as your Z score is bigger than that, you reject your null hypothesis. Okay. The critical value for T varies, so it depends on your sample size. But as long as your T score that you calculate is bigger than the T critical that you need to reject that, and you get that from the table, you would reject the null hypothesis. That tells you that number, that critical value for Z or T, is the value that means that the error is just under 5%. So you can reject the null hypothesis. If you want to, you can actually calculate. If you have the Z-score, you can go to the table and look up what the real p-value is for that particular Z-score. So not only, for instance, if it's 1.96, if you calculate a Z-score of 1.96, you don't have to go to the Z table. You know that your p-value is 0.05, same as alpha. That's why it's the critical value. If your Z-score is 2.1 instead of 1.96, well, now you can go to the Z table and look up what the probability of getting that high a t-score, a z-score would be if there were no difference in the two means, and that would be a smaller area because it'd be a different spot on the z table, and it would be smaller than 0.05, might be 0.04 or 0.03. So you could reject the null hypothesis immediately because you know it's less than 1.96, or you could go to the z table and look up exactly what the p-value is going to be. And you know that if your z-score is more than 1.96, then your p-value is going to be less than 0.05. And the bigger the t-score is, the smaller the p-value is. And you want that p-value to be less than 0.05, right? The critical value being bigger than the critical value and being the p-value being smaller than 0.05, they go together. Okay, so let me see. Yeah, I know my battery's getting low, but we're gonna be calling this a day soon, a night soon. I think I can get through this for now. Okay, let me just open database. Let me see, open recent. I want to see if I can't find. Let me see if I can't find NC birth. Okay. Let's open this. Okay, this is this might be one of the files that we might put up for you guys to work with. Oops. Oh no. Why did it do that? That must not be a SPSS file. NC birth 809. Okay. Nope, those are doc files. Let me get to it and then we'll be able to. Okay, here we go. I'll use that one. That one should work. Assuming it opens. Let's see if it did open. Oh, there we go. It's open. Okay, so in this case, This happens to be 800, randomly selected 800 births that took place in North Carolina during a period of time. This column here is a numerical variable. Now, remember that all of these calculations that we do use numerical variables. Okay, so we're down to about 4%. I'm going to get through this real quick. So our mother's age is listed here. I'm going to go up here, analyze, compare means, and I'm going to go to descriptive statistics and explore. And I'm going to ask it to find the average for the age of the mother for these 800 North Carolina births. Okay, statistics going to be 0.95%. I'm going to say okay. And it's going to give me the mean, it's going to be the confidence interval, and so on and so forth, standard error and confidence interval for that calculation. Okay, I like running. I like running on empty. Just like in a car. You're one of those people that doesn't like when you get close to that zero on that gas gauge. That kind of like keeps your blood pumping. When you don't know if you're going to make it or not. Okay, so there's our mean, and there it actually calculates our confidence interval. This is a big sample size of 800. So our standard error is going to be pretty small. Right? There's the standard error is 0.216 years, and so on and so forth. So now I'm going to repeat this, and I'm going to do a single sample t-test. I'm going to go compare means. I'm going to go to one sample t-test. I'm going to tell it I want to compare the age of the mother, right, to a set value. And I'm going to say I want to compare, what did it come up to before? It came up to 26. I'm going to say that in New York, the average age of mothers that give birth in New York is 28 years old. My null hypothesis is that the same age the average age of the mothers in New York State is the same age as mothers in North Carolina. Mothers in New York, I know, I checked all of them, are 28. I only know the sample for North Carolina, so I'm going to use this sample to decide to run my t-test, my z-score, rather, my t-test or z-score. With a big sample, it's basically the same thing. I'm going to do this analysis to determine whether or not I can reject the null hypothesis. Well, let's see what I got. My t-score is 5. That's way bigger than what I would expect for this big a sample, right? And what's the probability of being wrong? My p-value is 0.000. It's less than 0.001. It's really what that says. So it means it's really unlikely that I would be wrong if I reject the null hypothesis. Okay, so my p-value is less than 0.05, and my t-score is way bigger than my t-critical, which for a sample size of 700, 800 would have to be like pretty close to 1.96 anyway. Okay, so you can use SPSS to do these analyses.